Welcome to lecture 14. This is week 3 and we are talking about basic concepts of optimization part 1. So, in our previous lecture, we started our discussion on optimality criteria for unconstrained optimization problems. And in this week also, we will continue with our discussion on optimality criteria for unconstrained single variable functions. So, let us quickly review of what we learnt in our previous lecture on optimality criteria for unconstrained single variable functions. If a function f x is defined in the interval a to b and has a stationary point at x equal to x star, where x is bound between a and b, then at x equal to x star, the first order necessary condition for optimality is the first derivative evaluated at x star will be equal to 0. So, df dx at x star will be equal to 0. So, that is the first order necessary condition. So, second order necessary condition for local minimum is the second derivative evaluated at x star will be greater or equal to 0. So, d square f dx square evaluated at x star is greater or equal to 0. Second order necessary condition for a local maximum is d square f dx square is less or equal to 0. We also talked about second order sufficient conditions, and second order sufficient condition for a local minimum is d square f dx square evaluated at x star is greater than 0, strictly greater than 0. Similarly, second order sufficient condition for a local maximum is d square f dx square evaluated at x star is strictly less than 0. Suppose at point x star the first derivative is 0. Let us consider the second derivative is also 0 and the first non-zero higher order derivative is denoted by n. That means, we are talking about first derivative, second derivative, third derivative up to n minus 1th derivative evaluated at x star is equal to 0 and the first non-zero derivative happens at nth derivative. Now, if n is even, then there will exist a local minimum or local maximum. A local minimum of f x at x equal to x star will happen if n is even and the nth order derivative is positive. A local maximum of f x at x equal to x star will happen if n is even and the nth derivative is negative. If the n is odd, then neither a minimum nor a maximum occurs at x equal to x star. In that case, the point x star will be known as point of inflection. So, what we can summarize is the first order necessary condition is df dx at x equal to x star is 0. Second order necessary condition is d square f dx square is equal to greater or equal to 0 or less or equal to 0, depending on we are talking about minimum or maximum. Second order sufficient conditions are strictly greater than 0 or strictly less than 0, depending on we are talking about minimum or maximum. Now, if the first derivative is 0, the second derivative is 0, we cannot make any comment. Then we go on taking higher order derivatives and we go on taking higher order derivatives until we get the first non-zero derivative. And let us say the first non-zero derivative happens at nth derivative. If n is even, then the point x star may be an extremum, that means it may be a minimum or maximum. The x star will be minimum if n is even and the derivative is positive. That means nth order derivative is positive and n is even. X star will be maximum if the nth order derivative is negative and n is even. If n is odd, then x equal to x star is neither minimum nor maximum, it is a point of inflection. Now, let us give a simple proof to these conditions. Let f x be a function of single variable x defined in the interval x greater or equal to a greater or less or equal to b. So, that means we are talking about a single variable function f x which is defined over the interval a to b. F x is differentiable to the nth order over the interval. If x star is a point in the interval, then you can write using Taylor's theorem as this, where epsilon represents a small distance around point x star. So, basically we are expanding the function f x around x star by Taylor's series theorem. So, then we can write f x star plus epsilon minus f x star equal to epsilon into first order derivative plus epsilon square by factorial 2 into second order derivative evaluated x equal to x star and so on and so forth. We have shown up to nth term, then there are of course n plus 1 order term, n plus 2 order term and so on and so forth. So, this is what we can write from Taylor series expansion of the function f x around the point x star. So, x star plus epsilon is basically a small deviation around x star. Epsilon represents a very small deviation. So, if x star is the local minimum of f on the interval a to b, then in the epsilon neighborhood f x star will have minimum value because x star is minimum. So, if x star represents a minimum, then around it, if I consider a region, then the function value of f at x star will be minimum. So, we can write the function value f x, the function value of f at any other point x is greater or equal to f x star. So, this has to be satisfied if x star is the local minimum. The above inequality represents that this term is greater or equal to 0, because x star is a local minimum. In other words, this term is greater or equal to 0. So, let us write again that expression. For epsilon sufficiently small, the first term will dominate the others, because epsilon is small. So, if you take square, it will be even smaller. Since epsilon can be chosen both positive and negative, the inequality will hold only when df dx evaluated x star equal to 0. So, this entire term is greater or equal to 0. Now, we know epsilon is small. So, as we go from first term to second term, from second term to third term, the contribution of each term decreases. The first term will dominate the others. Now, let us look at the first term only. The first term has epsilon and df dx. Now, choice of epsilon is arbitrary because it can be positive as well as negative. So, to force this entire expression greater or equal to 0, we must set df dx evaluated at x star equal to 0, and that gives you the first order necessary condition for optimality. So, continuing the same argument, we can write d square f dx square is greater or equal to 0 for x star to be local minimum. Why? Because epsilon square by factorial 2 is always positive. So, df square dx square must be greater or equal to 0 for x star to be local minimum. So, we get both first order necessary condition as well as second order necessary condition. Now, similarly, we can show that if x star be a local maximum, the same argument will hold, but with the inequality sign reversed. That means, if x star is a local maximum, then function value at x star will be greater than or equal to than any other point in the surrounding, and f x star plus epsilon minus f x star will be less or equal to 0. So, following the same argument, we will be able to show that df dx evaluated x star will be equal to 0 as first order necessary condition, and d square f dx square must be less or equal to 0 as second order necessary condition. Now, let us talk about higher order sufficient conditions. What happens when the first derivative is 0, second order derivative is 0, third derivative is 0, so on and so forth. So, we keep on taking higher order derivatives, and the first non-zero higher order derivative is n. So, nth order derivative is the first non-zero higher order derivative. So, then we can write f x star, we can write this expression because all other terms before this nth order term are all 0, because such derivatives for n minus 1, n minus 2, so on and so forth, they are all 0. So, we can write the expression as shown on the screen. If n is odd, then the right hand side can be made positive by taking epsilon positive, and it can be made negative by taking epsilon negative. This implies that this value f of x star plus epsilon minus f of x star can be less or equal to 0, or it can be greater or equal to 0 depending on the sign of epsilon. Hence, the function does not attain a minimum or maximum at x star, and x star becomes a point of inflection. So, by looking at this expression, we can say that if n is odd, since this value can be made both positive and negative depending on the value of or sign of epsilon, the point x star neither becomes minimum nor becomes maximum, and it becomes point of inflection. What happens if n is even? If n is even, epsilon to the power n is always positive. For sufficiently small epsilon, the sign of the above equation will be dominated by the first term. That means, this term, note that this term is always positive. So, whether this will be positive or negative will depend on this nth order derivative. So, if the term epsilon to the power n divided by factorial n and nth order derivative evaluated at x star is positive, that means, if the nth order derivative is positive, then f of x star plus epsilon minus f of x star is positive or greater than 0 and x star is a local minimum. So, this is sufficient condition. Similar argument applies for local maximum, where f of x star plus epsilon minus f of x star is greater than 0. Sorry, this is less than 0 when nth order derivative is less than 0. So, for local maximum, f of x star plus epsilon minus f of x star is less than 0 and this will happen when the nth order derivative is less than 0. So, this is the sufficient condition for local maximum to occur at x equal to x star. Now, let us take quickly few examples. Example 1, determine the maximum and minimum values of the function f x equal to minus x cube plus 3 x square plus 9 x plus 10. So, the first thing to do is to use the first order condition to find stationary points. So, take df dx and set that derivative equal to 0. If we do that, we get minus 3 x square plus 6 x plus 9 equal to 0. From this, we get the stationary points as x star equal to 3 and minus 1. So, we have two stationary points. We have to evaluate both the stationary points and check whether maximum occurs or minimum occurs. Let us take the second derivative. So, if you take the second derivative, d square f dx square equal to minus 6 x plus 6. So, you have to evaluate this second derivative at x star equal to 3 and x star equal to minus 1. So, that is what we have done here. Let us first take stationary point minus 1. This is the expression for the second derivative. Putting x equal to minus 1, we get the value of the second derivative as 12, which is greater than 0. So, x minus 1 is minimum. Similarly, by putting x equal to 3, we get the value of the second derivative as minus 12, which is less than 0. So, x equal to 3 is maximum. So, this is the plot of the single variable function. You check that x equal to minus 1, minimum happens, and x equal to 3, the maximum happens. The value of the function at x equal to 3 is 37, and the value of the function at f equal to minus 1 is 5. Let us take another example. F x equal to 12 x to the power 5 minus 45 x to the power 4 plus 40 x cube plus 5. We have to find out the maximum and minimum values of the function. We will proceed as usual, apply the first order necessary conditions and find out the stationary points. So, take the derivative of the function with respect to x and we get stationary points as x equal to 0, x equal to 1 and x equal to 2. We have thus 3 stationary points and we have to evaluate the second order conditions at all of these 3 stationary points to check whether the points are minimum, maximum or point of inflection. So, the second derivative d square f dx square can be taken easily and it becomes 60 into 4 x cube minus 9 x square plus 4 x. Now, let us find out the value of the second order derivative at x equal to 0, x equal to 1 and x equal to 2 and check the second derivative is greater than 0 or less than 0. We write the expression for the second derivative one more time. So, let us start with x equal to 1. So, the value of the second derivative at x equal to 1 is minus 60. So, it is less than 0. So, at x equal to 1 a local maximum or relative maximum occurs, because the sufficient condition for maximum to occur is the second derivative will be less than 0. The value of the function is 12 at x equal to 1. At x equal to 2, the value of second derivative is 240. You can find that out by simply putting x equal to 2 in this expression. So, second derivative is positive, hence x equal to 2 is a relative minimum or local minimum and the value of the function at x equal to 2 is minus 1. Now, let us take x equal to 0. If we put x equal to 0 in this expression, we see that the value of the second derivative is 0. So, we cannot make any comment at this stage, we must take higher derivatives. So, let us take third order derivative. So, if I take third order derivative and evaluate the value at x equal to 0, I get (60 into 4) is 240, which is greater than 0. So, the first non-zero second order derivative, first non-zero higher order derivative happens at n equal to 3. So, third order derivative is the first non-zero higher order derivative. So, it is third order derivative, that means n equal to 3. So, x equal to 0 is neither a maximum nor a minimum, this is a point of inflection. As a third example, let us take the case of critical insulation thickness. Consider this example. You have a pipe through which steam flows. Let us consider there is a copper pipe. So, inside a copper pipe the steam flows, and to arrest heat loss you are putting insulation around it. Now, as you go on increase the insulation, the resistance increases. The thermal resistance due to heat conduction increases, but at the same time the thermal resistance due to heat convection may decrease due to increase in heat transfer area. Please note that as you go on increasing the insulation thickness, the heat transfer area, which will be 2 pi R2 into L, where L is the length of the cylindrical pipe, will increase. So, there are two resistances involved. One is resistance due to heat conduction, and there is resistance due to convection. So, total heat loss or heat transfer is T1 minus T infinity, T1 minus T infinity, the driving force, divided by the total resistance. Now, the conduction resistance increases as you increase the insulation thickness, but the convection resistance decreases as we increase the insulation thickness. So, at critical insulation thickness, the total thermal resistance is minimum. Beyond that, if I add on, if I go on increasing the insulation thickness, heat loss will be less. So, we need to know what is the critical insulation thickness where the total thermal resistance is minimum. So, for that I have to minimize this expression, which is nothing but the sum of the total resistances. Note that the total thermal resistance is a function of R, where this R is the insulation, this R represents insulation thickness, this R. So, should I stop here or should I go on increasing like this? So, smaller one is the inside radius and R is the radius which represents this distance. So, it represents the insulation thickness. From this value of small r, you can find out the insulation thickness. So, we must find out the R that minimizes the total thermal resistance. So, if you look at the expression, this is a single variable function of R. Let us use the first order necessary condition. So, take the derivative of total resistance with respect to R and set that equal to 0. If we do that, we get the value of R which minimizes the total resistance R total, which is R equal to K by H. So, now we need to know whether this critical radius or the critical insulation thickness R C equal to K by H is indeed minimum point or maximum point or point of inflection. So, we must take the help of second order condition. So, take the derivative, second derivative. If you take the second derivative and evaluate it at r equal to k by h, you get the expression as 1 by 2 pi L k cube by h squared. Please note that this term is always positive, because it involves pi, which is always positive. It involves L, which is the length of the pipe, which is always positive. It involves k cube, which is thermal conductivity. K is thermal conductivity, is always positive, and heat transfer coefficient H is always positive. So, the second derivative is always positive. So, the insulation thickness R equal to K by H is indeed a minimum point. So, the total thermal resistance is minimum at R equal to K by H. With this, we will stop lecture 14 here.